Welcome to the video for Lecture 27. This video covers two methods for tuning controllers. This video will also discuss several process specifications and go over the Cohn-Kuhn method for finding the settings Kp, tau I, and tau d for different combinations of proportional, integral, and derivative control, and finally the Ziegler-Nichols method for finding Kp, tau I, and tau d. Many process control characteristics are based on the physical properties of the process and equipment used. For example, fluid heating performance is different for a typical residential water heater with a 50-gallon tank using on-off control compared to a tankless residential water heating system. Mixing systems will have different responses depending on tank volume and the material flow rate because they affect the process time constant. We covered a variety of processes that could be modeled with first-order ordinary differential equations. Higher-order responses were needed for interacting tank systems, and higher-order responses were produced when we used proportional plus integral control. I also made the point that time constants for the process, sensor and feedback element, and the actuator could be important. In some cases, only the process time constant will be important. All of this depends on the process characteristics. Finally, we sometimes need to consider process delays and dead time. We used a sample line delay with the bioreactor problem. If you are responsible for process control, you will need to decide what type of process control you will use. Many processes use on-off control where the user sets the set point and the switching differential, and the controlled equipment is either fully on or fully off. If you choose to use a large switching differential, you will have less cycling, but you'll have larger fluctuations in the process output value. If you choose to use a small switching differential, the equipment will cycle on and off more times, but the process output will not fluctuate as much. Excess cycling can be hard on equipment as it goes on and off. We are seeing a move away from on-off control towards more PID control if the device being controlled can be adjusted continuously. A 2013 research report reported that an animal feeding operation using 20 horsepower motors on 2 well pumps using on-off control used more energy than an operation using 2 20 horsepower motors on well pumps using variable frequency drives that ran the pump motors at just the speed needed to provide the water needed. The operation with the standard on-off control had each pump turned on and off roughly 170 times each in a 24-hour period. The operation that had the 2 variable frequency drive well pump motors only turned on and off a total of 38 times over a 24-hour period. The one pump turned on and off only 8 times in the 24-hour period. The report indicated that the operation with on-off control could save over $2,300 per year by installing variable frequency drive controls on the well pumps. To be able to use PID control, the actuator needs to be continuously adjustable. For example, the adjustable diaphragm flow valve shown in the slide could be continuously adjustable. However, the 2-position solenoid valve you used in the actuator lab cannot be used as a flow controller. Relays turn motors on and off. You would need a variable frequency drive actuator to drive the continuously adjustable motor speed you might want. One aspect of good control is staying within user-defined tolerance limits. For example, a person using the fluid heater we've been studying could specify that she wants the fluid temperature to be 41.5 degrees Celsius plus or minus 0.3 degrees Celsius. With this type of process performance specification, the outlet temperature can be monitored to see what percentage of the time the outlet temperature is within the specified tolerance and what hopefully small amount of time the outlet temperature is outside the specified tolerance limits. Within this course, the variables we can adjust when we use PID control are the proportional gain Kp, the integral time tau I, and the derivative time tau d. So how do we find the settings for Kp, tau I, and tau d to get good PID control? The selection of these values is called controller tuning. In addition to maintaining the process output within some specified tolerance, good control is assessed by how the system responds to a step change in either the set point or a process input. The size of the step change will depend on the expected set point or load changes that the process would be expected to experience. So process tuning is used with PID control and is an effort to find the values of Kp, tau I, and tau d to use to calculate the actuator process adjustment needed to get the process output to be within desired tolerances. The actuator must be continuously adjustable, and you are trying to find the best settings of Kp, tau I, and tau d to optimize the process and get good control. The reasons for striving for good control are to improve the product quality by maintaining the process output within a tighter tolerance and making the process output more uniform more of the time. When you produce more product within the desired performance limits, you will have a process that saves time, money, and process inputs, and you want the output to return quickly to within specified tolerances when the set point is changed and when other process inputs or loads change. Here are the definitions of good control we will use in this class when setting the values of Kp, tau I, and tau d. In general, most process operators want the response to a step change in either the set point or a variable process input to produce a maximum overshoot of 25% or less. The other good control performance response is that the decay ratio is 1/4 or less, again in response to a step change in one of the inputs. There are other process control indicators, but they are beyond what we have time for in this class. You may run into cases where the user will set other performance criteria, but the maximum overshoot and decay ratios are the most common criteria. With good control, the output will return to within process tolerance limits fairly quickly. Now that we have some dynamic performance limits, how do we find values of Kp, tau I, and tau d that will produce good control? Well, one method is trial and error. It is always an option. Another approach that could be used is to develop a process model like those that we have been using in this class. Then you can use various modeling techniques to find good values of Kp, tau I, and tau d. In industry, there are many processes for which no one has developed a process model. The process physically exists, and people need a way to set new controllers or adjust old controllers so that the process has good control. We will talk about two methods. They are the Cohen-Kuhn method and the Ziegler-Nichols method. The method to use will depend on whether the controller is disconnected during test runs to collect data needed, or whether the controller is connected. If you use the open-loop method, the controller is disconnected and the response will be S-shaped, and you'll be using the Cohen-Kuhn method. If you use the closed-loop method, the controller is kept in the process controlling the system. The response wanted is sustained oscillations, and you'll be using the Ziegler-Nichols method. This slide shows the S-shaped response that an open-loop process with the controller disconnected will produce in response to a small step change. With this graph, you can use the Cohen-Kuhn method. This slide shows the desired sustained oscillations response that a closed-loop process with the controller connected will produce in response to a small step change. With this graph, you can use the Ziegler-Nichols method. So if we plan to use the Cohen-Kuhn method to collect information to find the values of Kp, tau I, and tau d, we need to disconnect the controller. This means that there will not be any process adjustment made when there is a change in one of the inputs. With the controller disconnected, we will make a small step change of magnitude m to one of the inputs. Then we measure the process output C of t and plot the results. Hopefully you'll get the S-shaped response shown here. We will use the output information to find some values that we will use to calculate the recommended values of Kp, tau I, and tau d. The analysis can be done either graphically, the way we will do things, or they can be done analytically. The first step is to plot the process response to a step change m with respect to time. Then we draw a tangent to the inflection point. Then we begin to find some of the data we need. First, we need to find the long-term process output value, which we will label as C infinity. Then we find the parent transport lag. The transport lag, Td, is the time between the time t equals 0 and the time when the tangent crosses the 0 output. The next thing to find is the process time constant t. The process time constant is the time between when the tangent crosses 0 and when it crosses infinity. So from this graph, we can find C infinity, Td, and t for an open loop process that had a step change of magnitude m. Now that we know m, c infinity, td, and t, we can calculate the tangent line slope s. S equals c infinity divided by t. We can also calculate the process steady state gain k. K equals c infinity divided by m. Now knowing k, td, and t, we can calculate the values we should use for kp, tau I, and tau d. The equations used depend upon what type of control is being used. This slide shows the equations to use to calculate kp if using proportional control only, and the equations to calculate kp and tau I if using proportional plus integral control. The equations are also in the course packet. This slide shows the equations to use to calculate kp and tau d if using proportional plus derivative control, and the equations to calculate kp, tau I, and tau d if using proportional plus integral plus derivative control. Let's look at an example. We disconnected the controller and made a unit step change in one of the inputs. With the unit step change, m equals 1. We plotted the S-shaped response. We see from the graph that c infinity is equal to 1. Now we draw a tangent to the inflection point and see that the transport lag time td is approximately 0.33 minutes. Next we find the process time constant t. We see that the tangent crosses c infinity at about 1.67 minutes. The process time constant t is equal to 1.67 minutes minus 0.33 minutes, so t is approximately 1.34 minutes. Now we can calculate the tangent slope s over t. We get 1 over 1.34, so the slope is 0.75. And we can calculate the process steady state gain k. K is equal to c infinity divided by m. Both c infinity and m equal 1, so k equals 1. Now we have the information we need to calculate the controller settings. We know that the transport lag time td equals 0.33 minutes, the process time constant t equals 1.34 minutes, and the process steady state gain k equals 1. Assuming that we are using PID control, we use these three equations to find kp, tau I, and tau d. And after we put in the numbers, we find that kp equals 5.7, tau I equals 0.67, and tau d equals 0.11. Let's see what the controller settings should be for our water heater example. Using our block diagram, we see how the outlet water temperature T behaves if the actuator input experiences a step change of magnitude m. The actuator input function is a step change m over s. Here's the transfer function describing the measured output temperature Tm for a given actuator input P. Using the given data shown, we get the response on the next slide. Here's a graph of the water heater output temperature in response to a unit step change in the actuator. From the graph we can see that C infinity is 0.12. Then we add the tangent line and the vertical line when the tangent line crosses C infinity. We can find that the apparent transport lag time, Td, is 3 seconds, and the process time T, which is 142 seconds. Then knowing C infinity and the process time T, we can calculate the slope. The slope is 0.000845. Finally, we can calculate the process steady state gain K, which is 0.12. So now we know M, Td, and T. Assuming that we are using proportional plus integral control, we use the equations shown to find Kp and tau I. In this case, Kp equals 355 and tau I equals 10. These are quite different from the numbers I used before. Here is a graph of the two responses using PI control and a unit step change. The blue line is the result using Kp equals 83 and tau I equal to 60. We don't get much overshoot, but it takes much longer to get within 5% of the final value, over 300 seconds. The green line is the response we get using Kp equal to 355 and tau I equal to 10. We have a higher overshoot, approximately 25%, which is acceptable for good control, and the response settles down to within 5% of the final value much faster, around 100 seconds. so the Cohn-Kuhn method produced good process control results. The other method for controller tuning is the Ziegler-Nichols method. This method is sometimes called the closed loop method because the controller stays in the process loop. The controller is set up to run using proportional control only, and the process is subjected to a small step change to produce sustained oscillations in the response. When using the Ziegler-Nichols method, we are looking for the ultimate proportional gain, Ku, and the ultimate period, Pu. The ultimate proportional gain is the gain setting used to produce the sustained cyclical process output after the process is subjected to a small step change. The ultimate period, Pu, is the period of the oscillating process output. Please remember that the period is the time for one complete cycle. To collect data for the Ziegler-Nichols method, the integral control and the derivative control parts of the controller are disabled. If the integral part of the controller cannot be disabled, then set the value for tau I to some very large or maximum value. If the derivative control cannot be disabled, set tau d to some very small or minimum value. Then select a Kp value. Disturb the system with a small step change and record the process response. If you don't get sustained oscillations, increase Kp and disturb the process again. Repeat the setting of Kp, disturbing the system and observing the response until the process output is a sustained oscillation. You do not want oscillations that continue to get larger or blow up. You want sustained oscillations. Once you get the system to produce sustained oscillations, you know Ku. Ku is the last Kp value used. Then you look at the process response and determine the ultimate period of the sustained oscillations in the process output. Once you know Ku and Pu, you can find the controller settings. Here are the equations to find Kp, tau I, and tau d, knowing Ku and Pu. You can see from the equations that Kp is some fraction of Ku, and tau I and tau d are related to the ultimate period Pu. These are simple calculations. When working with real industrial processes, it is important to take some precautions. Here are 3 recommendations when adjusting a process to collect data to be able to use the Ziegler-Nichols method. Pulse changes are recommended, where you step up to create one step change and you step down to create a second step change. By alternating step changes around the normal steady-state conditions, you avoid getting far from normal conditions. Also, by using small disturbances, you avoid saturating system components. This brings me to the end of the Lecture 27 video. Write down any questions you have and bring them up in class.